Welcome back, everyone. We are going to start our new unit, nuclear chemistry. So the first slide here is going to be the standards we're going to cover throughout this unit. We're going to differentiate between chemical and nuclear equations. We're going to explain and compare nuclear reactions, which is radioactive decay, fusion, and fission, and other energy changes associated with them in their safety issues. And we're going to differentiate among the various forms of energy and recognize they can be transformed from one form into another. The essential question, why is it important to understand the impacts of fusion and fission? Today, though, our main goal is we're going to describe the three main types of nuclear radiation. We're going to describe the types of decay as a radioisotope undergoes. We're going to identify alpha, beta, and gamma radiation in terms of components and key particles. And you're going to apply your knowledge of radioactive decay to actually write balanced nuclear equations. I promise you they're much easier than balanced chemical equations, though. So off we go to nuclear chemistry. So the chemistry, an ice age baby. In 2007, a reindeer herder in north central Russia thought he spotted the remains of a frozen reindeer. What he found was a perfectly preserved baby woolly mammoth, about the size of a large dog. The only thing missing was its shaggy coat. Woolly mammoths are an extinct species related to modern elephants. These mammals had curly tusks and long hair, and they lived on Earth from about 1.8 million years ago until they went extinct 11,500 years ago. So, how do scientists know when this mammoth lived and died? So, when we start talking about nuclear reactions, we'll be able to figure out how they could figure out when this mammal lived and died. All right, so let's talk about what radioactivity is. So, elements are going to undergo breakdowns, and they're going to give off rays and particles when they do that. The rays and particles that are given off are referred to as radiation. Nuclear reactions, though, are different than chemical reactions. So if you remember in chemical reactions, we were talking about the electrons. How the electrons pair up and bond to form compounds, which then led us to equations. But nuclear chemistry is different, and radioactivity especially, because we're talking about the change in the nucleus, the nuclei change, which means there's going to be a change to the protons this time and neutrons instead of the electrons. So we are going to be copying the green that you see here. So radioisotopes are unstable isotopes that gain stability when the nuclei undergo changes that are considered unstable or radioactive. So you'll see this term, unstable, refers to something being radioactive. It's not stable, and it's going to try to get that way in any means possible, which means it's going to give off those rays and particles that we just talked about. So nuclear reactions. This is going to change the composition of an atom's nucleus. So remember, its goal is trying to be stable. So the stability of an isotope is based on the ratio of protons and neutrons within the nucleus of those isotopes. Too many or too few neutrons will cause an isotope to be unstable, which then emits that radiation in the forms of particles and rays. So the picture you see here was an actual detonation of a nuclear bomb. This occurred, they were practicing these before and after World War II. So you can see the detonation occurred underwater. So they were able to track and see how well the bombs worked. So how do I know an element is radioactive other than I'm being bombarded with radiation, which is not a good thing? And you can't see that, so you wouldn't really know either. So all elements with atomic numbers greater than 83 are considered radioactive. They have no stable isotope. These elements are going to naturally decay, releasing those particles, to form a more stable isotope. So then they are much more stable, and then they can exist in a much easier form. Now, uranium is the last naturally occurring element. So everything after element 92, remember, was man-made, and a lot of those are radioactive. So let's talk about the three types of radioactive decay that you need to know about. You have the first one, which is alpha decay, which is going to be shown by the emission of a helium nucleus. So you're going to see the symbol of helium along with the mass number and the atomic number. Now, this is a characteristic of a heavy nuclei. I do want you to copy down this equation you see here. So you've got your uranium-238 on the left, and then it's got the thorium-234 plus the helium nucleus. So you can see the helium nucleus there is the He with the 4 and the 2. So that's going to be an indicator that you have alpha decay. The second type is going to be beta decay. This is going to be the emission of an electron during the conversion of a neutron to a proton. Well, we weren't really talking about electrons, but in this, it's how it's indicated. Instead of using the symbol for beta, which looks like a weird B, they're going to use an electron, so they're going to use an E instead. So same thing, you've got carbon 14 here on the left, and then you have the nitrogen 14, and then this is the indicator here that this is a beta decay. It has the E with the 0 on top and the -1, and we'll come back to why these structures look so familiar. The last type of decay is gamma rays. Now, it's explicitly stated it's a ray and not a particle. Now, there's actually no equation for gamma rays because it doesn't change the mass, nor does it change the element, so there's no need for an actual equation. So those are going to be the three main types of radioactive decay that you do need to know about. Now, which one's stronger, which one's weaker? Let's talk about that. So just to give you kind of a background though, so you know, here's a table showing you the three different types of decay and how they're written. So alpha, once again, it's got that helium nucleus, or the Greek letter sigma. Then you have the charge is +2. The mass is 4 on top. It has a very low ability to penetrate, to reach. It's very easily stopped pretty much. So you can stop alpha decay with paper or clothing. So if I knew that alpha decay was coming toward me, if I held up a piece of paper, it would block that decay. It wouldn't reach me. Now the second type is beta. Remember, that's the electron. Now the charge is -1 for an electron. The mass, it's showing me a number here, 1 divided by 1836. But on the actual symbol, it's showing a 0 because this number is so very small. It's just written as a symbol. Now it's a little bit stronger, but I can still stop beta decay with aluminum foil. So it wouldn't be able to penetrate aluminum foil, so then it would not reach me. And then the last type, gamma, once again, there was no change in charge, no change in mass. Now, gamma is the strongest and the most dangerous, but you can still stop that with lead and concrete. Now, you don't want radiation to hit you, and we'll talk about this later as well, because it can cause mutations and kills your cells in your body, which is a bad thing if you remember from biology. So here's a nice graphic just breaking it down. Alpha, stop by paper. Beta, stop by wood. Gamma, concrete or lead. So let's get into the actual application today, writing nuclear equations. So remember, nothing disappears in chemistry. There's no magic. So everything's going to be accounted for, and that's going to help us write these balanced equations. So the sum of the mass number and the sum of the protons, or the atomic number, must be the same on both sides of the arrow. Now, if you don't remember this is how we wrote elements with the mass number on top, the atomic number on the bottom, and then the symbol. So uranium-238 with 92 protons, thorium-234, mass number, the atomic number is 90, and then we can see here this is going to indicate alpha decay, which is the helium, with the 4/2. So all of these things are going to add up. So if I look at this on the left, I've got 238 for my top number. When I add the two numbers up on the right, I also get 238. On the left, the bottom number is 92, and then on the right, if I add up 90 and 2, I get 92. This is extremely important because we're going to be using this to solve. Now, leading up to this, we talked about things that were on the left were reactants. The things on the right are products. Well, in nuclear chemistry, they also have a second name. If it's on the left of the arrow, it's the parent or the starting isotope. The element that comes out, or the isotope that comes out, is what we call the daughter. So you're going to hear parent and daughter when we talk about nuclear equations and the type of decay. So once again, the numbers match up and everything is equal. So we can use this to help us solve. So I'll show you another example with beta emission. As you can see here, uranium-239 on the left. So you have your 0 plus 239 gives me 239. And then -1 plus a 93 gives me 92. So then everything is equal. So remember that in beta, the top number, the mass number, will not be changed, but the bottom number should increase by 1 depending on what you're working with. For the daughter, it's going to increase by 1. So let's see if we can solve this example. So go ahead and write it down. This is boron 10. So what is the radioactive isotope produced in the following bombardment of boron? So I'm giving you the parent, boron, which is 10, atomic number 5, which you find on the periodic table. We don't know the type of isotope that's going to be made. So then we're going to take and use this information we have here to solve. So really, you're just subtracting. So the way you do this, the way I recommend it, is you do the bottom number first, because that's going to give you your element. So I'm going to do 5 minus 2, which is going to give me a 3. I go to the periodic table. Element number 3 is lithium. And I'm going to do the top number, 10 minus 4, which is going to give me a 6. So I'm going to end up with the daughter being lithium 6. That's all there is to it. You're literally subtracting or adding to find whatever you're missing. Just need to remember that where the stuff goes correctly. Remember, the mass number is always going to be on top, and the atomic number is always going to be on the bottom. So let's do a couple practice problems. We'll do the first one together, then I'll have you guys try the second one, and then I'll show you the answer. So the question says, write the nuclear equation for the beta emitter cobalt-60. That's a capital C, lowercase o. And then this is a dash, not a negative. So this is going to be the mass number. So this is going to be my top number. So it's telling me it's going to be a beta emitter. So I know the type of decay. It's going to be beta. So I'm going to be using the E0 negative 1. The cobalt-60 is my parent. So I'm going to start off with that. So cobalt-60, I went to the periodic table. I found the atomic number is 27. I know that it's going to go through beta decay. So my type of decay is going to be the electron, so the 0, negative 1. So now I need to find what I'm missing, the daughter. So I'm going to do the bottom number first. So 27 minus a negative 1, which makes it positive. So it's really going to be 27 plus 1, which is going to give me 28. So I go to the periodic table. Element number 28 is nickel. And then I do the math for the top. 60 minus 0 is 60. That's all there is to it. I found the daughter of that reaction. So go ahead and try the second one. Write the nuclear equation for the alpha decay of plutonium-244. So once again, alpha decay. So it's telling me I'm going to be using the helium nucleus in this one. So I start off with plutonium-244, and I go to the periodic table, and plutonium is element number 94. So I draw that for my parent. I draw the arrow, and now I know the type of decay is going to be the helium atom or alpha decay. So I'm going to put that in place. So now I'm going to solve. Now you'll notice the helium isotope part is going to be here in the front this time, where in the last question the beta was at the end. It doesn't matter. If I put the beta first or if I put the daughter first, it does not matter as long as it's on the right side of the arrow. It doesn't matter the placement, which comes first, which comes second. You can put the decay first, you put the daughter first, whatever's easiest for you. So now I do my math. 94 minus 2 gives me 92. So I go to the periodic table, that is uranium. Then I'm going to do 244 minus 4, which is going to give me 240. So I have uranium-240 is my daughter isotope. All right, give you a little more practice and see how we're doing with this. So go ahead and solve these 4, and we'll come back together in about a minute to see how we do. I'm going to pause the video, actually. All right, so let's work our way through these. So starting off with the bottom number, 13 minus a 14 should give me negative 1. 25 and 25 give me 0. So this type of decay is going to be beta. Now, the second question is a little different than what we've done. We're now going to find the parent. So my unknown is the thing on the left this time. So all I'm going to do is I'm going to add up what's on the right. So 93 plus 2, 95. 4 plus 2, 37, 241. So I get americium-241. The third one, cesium-140. Once again, it's going to be the E-1, which tells me that's going to be beta decay right on the end. So then I'm going to do 55 minus a negative 1, so I'm really adding. So it's going to be 56 for the bottom number, so that takes me to barium. Top number doesn't change because the beta decay has a 0. And then lastly, our old tried and true uranium-238. So I solve that's going to make it a alpha decay. Now, what you might notice is every time we have the beta, the top number never changes. So that's kind of a shortcut. So if you're given the parent and the daughter isotopes and you see the numbers are exactly the same, you automatically should be able to know that that's going to be a beta decay. So I'm going to have you guys do some more practice. On the next few slides are some section questions from the textbook I want you to work on under the notes. I will make the answer key available so you can check your work. This will not technically be a grade, but it will lead to what we're going to do tomorrow. That will be a grade, and we're going to try to practice uploading our work to see how that works on Focus. If you have any questions, I will be available Tuesday. I'll have some live chats set up, and I'll let you know when those are occurring if you want to ask me questions. or you can always shoot me a message on Teams or Remind. I hope this was really helpful and that you guys are ready to start our virtual learning. I'll talk with you soon.